So the next part that we're going to talk about is the mean value theorem and monotonicity. So first we'll start with the mean value theorem. So the mean value theorem is a more generalized version of Rolle's theorem. So if we go back to what Rolle's theorem was saying, it's that if I have a continuous function where the endpoints give me the same function value, then there's some point where the derivative is 0. So the mean value theorem is a more generalized version of that. So what this says is, let's assume that f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b. So the same qualifications that we needed for Rolle's theorem we're going to use here for the mean value theorem. I need my function to be continuous and I need it to be differentiable. Then there exists a c in the interval such that the slope of the tangent line at c, so the derivative evaluated at c, is the slope of the secant line connecting the points where we have a and b. So this is the mean value theorem. It just says that if I have a function that's continuous from a to b, so here's a, here's b. Let's say this is my function. If it's differentiable with this, which this one is differentiable, it says that I can make a secant line, and that's this slope here, f of b minus f of a over b minus a. It says that the slope of this secant line corresponds to the slope of some tangent line for a value between a and b. So let's see, probably right here. That has the same slope, so there's our c. That's what the mean value theorem is telling us, is that if I connect the 2 points and draw my secant line, there's a point in between a and b where the tangent line has the same slope. So that's what this is saying. Now again, Rolle's theorem is a special case of this where we're talking about the slope being 0. But that's the mean value theorem. So connect the 2 points, that's my secant line. I can find somewhere that has the same slope. So for example, let's consider f of x is x squared minus 2 on the closed interval from 0 to 3. Let's verify the mean value theorem on this interval. So when we say verify the mean value theorem, we're saying that we need to find a c. So what this means is that we need to find c such that f prime of c is equal to f of 3 minus f of 0 over 3 minus 0. That's what the mean value theorem says, is that, 0 to 1, 0 to 3, is that this should exist. So let's go ahead and find it. Graphically, x squared minus 2, that's just a parabola that's been shifted down 2 units. So there's my parabola. Whenever I plug in 3, I'll get 9 minus 2, which is 7. And whenever I plug in 0, I'll get 0 minus 2, which is negative 2. Okay, so what the mean value theorem says is that I should be able to find a point between 0 and 3 that has the same slope as the secant line that connects the two. So there's my secant line. We can actually do this algebraically. It says that f prime of c should be, what was that, 7 minus negative 2 over 3. So 7 minus negative 2 is 9, 9 over 3 is 3. So I'm looking for where the derivative is 3. Well, can we find what the derivative is? Sure, take the derivative here. F prime of x is just 2x. So if I plug in c, I'll get 2c. Divide both sides by 2, so c is 1.5. So that tells me, if I look up here where 1.5 is, it's right there, and there's the point on the curve, it says that the tangent line at that point has the same slope as the secant line. So we did verify it. There is a point, it's 1.5, it's definitely between 0 and 3, where these two lines have the same slope. So that's the mean value theorem. That's the technical version of it and what it means. Now, how are we going to use the mean value theorem? We're going to use it to say a lot about slope. So the mean value theorem tells us a lot about slope. Now slope has been a big deal in this class so far, because that's what the derivative is talking about the slope of the tangent line. But let's go through the 4 things that the mean value theorem can tell us. First thing, if f of x is differentiable and f prime of x equals 0 for all x in an interval, then f of x is constant. F of x is just some constant k. So for some k. Because of what the mean value theorem states, we know that if f of x is differentiable and the derivative is 0, then the original function had to have been some constant. So if you know that the derivative is 0 for all x in some interval, then the original function had to be a constant. Which kind of makes sense. I mean, think about the function just f of x equals k. The derivative is definitely 0 everywhere, so if the derivative is 0, then we can go backwards with it. The function was just a constant. The second thing, we say that f of x is increasing on an interval from a to b if f of x1 is less than f of x2 for x1 less than x2, both in the interval from a to b. So we've done this before. We said that f of x is increasing if, as I go from left to right, my function values are getting larger. So something like this. We're going to stop thinking about it in this way. Because of the mean value theorem, what we can say is that a function is increasing if the derivative is positive. So this is the big thing, or one of the big things that the mean value theorem tells us, is that a function's increasing if the derivative is positive. Another big thing we can say, f of x is decreasing on an interval from a to b if f of x1 is greater than f of x2 for x1 less than x2, both in the interval, which we've done before. We've written this down before. Pictorially, this is saying that as I go from left to right, the function values are getting smaller, so something like this. From now on, because of the mean value theorem, whenever we see decreasing, we say a function is decreasing if the derivative is negative. So if f prime is negative, then it's decreasing. Alright, so those are the main 3 things. The 4th thing that I want to say about the mean value theorem is really a definition. It's a definition for monotonic. So a function f of x is monotonic. So the word monotonic, mono means one, so we're talking about one thing here. So we're saying that f of x is monotonic on an interval from a to b if it is either increasing or decreasing, not both, on the interval from a to b. So a function is monotonic if it's either increasing or decreasing on an interval, not both. So I can't have that it's increasing for a little while and then decreasing for a little while on that interval. I need that it is definitely increasing always. So let's do some examples here. Example 1. Let's show that f of x is 2e to the 2x is monotonic on all real numbers. So being monotonic means that it's either increasing or decreasing on whatever interval we're looking at. Here the interval is all real numbers. So I want to show that it's either positive, the derivative is either positive or negative always. So let's look at the derivative. To take the derivative, I'm going to have to use the chain rule. So my derivative is going to be 2e to the 2x times 2, which is 4e to the 2x. This function is always positive. It doesn't matter what function or what number you plug in for x. This is always greater than 0. So I just took the derivative, showed that it was greater than 0. This means that my original function is always increasing. Therefore, f of x is monotonic. Monotonic. Because it's always increasing. It never decreases or anything like that. So it's always increasing. That means that it's monotonic. Okay, so let's look at a different function. How about when is the function f of x, which is 2x minus 4 squared, decreasing? So whenever you think of decreasing, what you want to think in your head automatically is f prime being negative. So this is the same thing as saying f of f prime of x is less than 0. That's the question we're asking, is when is the derivative negative? That's the same thing as saying the original function is decreasing. Well, let's find the derivative. This is a chain, so I have 2x minus 4, then x squared. So my derivative is 2 times 2x minus 4 times 2. So 4 times 2x minus 4. I want to know when is that less than 0. Well, let's just solve this. This is just a linear equation with an inequality. First thing I'll do is divide both sides by 4. So 2x minus 4 is less than 0. Add 4 to both sides. 2x is less than 4. X is less than 2. So when is this function decreasing? F of x is decreasing on the interval from negative infinity to 2. So all x less than 2, it's decreasing on that interval. Again, whenever you see decreasing, you want to think f prime is negative. That's what we want to think here. Okay, so now that we know a little bit about increasing and decreasing, what we want to look at are critical points, deciding if a critical point is a maximum or a minimum. So we know what critical points are. Let's recall that. A critical point, or a critical value, maybe we should say that. A critical value, A, occurs where f prime of A equals 0 or f prime of A is undefined. So we're going to find our critical values where either the derivative is 0 or it's undefined. Then we want to classify them. We want to decide, are these local maximums or local minimums? So before we did absolute, an absolute maximum or minimum is over the whole picture, what's the largest value. But local minimums or maximums, we're saying just in that little area, is it a maximum or a minimum? So our critical values, local maximums or mins. Let's think about the picture that we're doing here though. Let's say this is my function. Critical values are where the derivative is 0. So So there's going to be one, let's call that A. There's another one that's called B. So these are my two critical values for this one. Which one is a local max and which one is a local min? Well, local max means that my y value is the largest relatively speaking to that point. So this is a local max. Here, you can see my y value is kind of the smallest in this little area, so this is a local min. As far as slope goes, what's occurring at this local maximum? What is the slope of f of x doing? Well, it's positive and then it becomes negative. So a local max, we have that f prime of x changes from positive to negative. And you can see this in the picture. My slope went from positive to negative. What's happening in my local min? Let's see, the slope is negative and then it's becoming positive. So f prime of x changes from negative to positive. So if we want to decide if critical values are local maximums or minimums, we're going to test what happens to the derivative. Does it go from positive to negative or negative to positive or neither? So here's the test that we're going to look at. Step one is we're going to find the critical values. We're going to do that by looking where the derivative is 0 or undefined. Next, we're going to plot these on a number line. Next, we're going to test points in between and plug into f prime. Then we're going to say if the slope went from positive to negative, then we have a maximum. If it went from negative to positive, then we have a minimum, which we just did. So let's do an example. Well, one more thing I do want to say. You can also read off, if you wanted to, so just kind of start. You could do this if the question asks. You could read off intervals of increasing and decreasing from this number line. So this number line is going to be a big deal for us. This number line is going to tell us where local maximums and minimums occur. It's also going to tell us where we have intervals of increasing and decreasing. So this is going to be a lot, and we definitely want to understand how this works. Example 1. Let's determine the local maxes and mins of the function x cubed minus 75x plus 5. So we want local maximums and minimums. So first thing I'm going to do is calculate the derivative. So the derivative here is 3x squared minus 75. Is this ever undefined? Well, this is a polynomial, so no. Next, where is it 0? That's 3x squared is equal to 75. So x squared is 25, which tells me x is negative 5 or 5. So I found where the derivative is 0. Now I'm going to plot that on a number line. And I'm going to be careful. I'm going to label this f prime, because that's what we're looking at. So where was it 0? It was 0 at negative 5, and it was 0 at 5. So those are the two places that my derivative was 0. Now the next part comes to test points in between these. So I need to pick a value in this interval, and this interval, and test them. So think of something that's less than negative 5. Well, how about negative 6? Let's test that. And I'm putting this in f prime. So if I plug this in f prime, I'm going to get 3 times negative 6 squared minus 75. Well, let's see. 6 squared, or negative 6 squared is 36. 3 times 36 is definitely larger than 75, so this is positive. I don't care at all what the number is. All I care is that it's either positive or negative. So since it was positive, I'm going to come over here and put a positive. Next, I'm going to pick something between -5 and 5. An easy number would be 0, so let's put that into our derivative. So 3 times 0 squared minus 75, definitely negative. Again, I don't care what the number is, I just care if it's positive or negative. And then lastly, something larger than 5, let's test 6. So 3 times 6 squared minus 75, positive. So I'll put a positive here. This tells me that, remember that f prime is slope, the slope went positive, 0, then negative. Then over here it was negative, 0, and then positive. So where do I have a local maximum? And where do I have a local minimum? Well, I have a local maximum at where x equals -5. Where do I have a local minimum? That would be at x equals 5. Tell me where the function is increasing. Well, let's see, it's increasing where the derivative was positive, so it's increasing from -infinity to -5. And then it's also increasing from 5 onwards, so from 5 to infinity. Now where is it decreasing? It's decreasing where the slope was negative, so from -5 to 5. So from this number line, we were able to read off local maximums and minimums and intervals of increasing and decreasing. So we had a lot here. Let's do another example. Let's find local maximums and minimums and intervals of increasing and decreasing of the function e to the x minus 2x. So we're looking for local maximums and minimums, intervals of increasing, decreasing. So we want to think in our head, we're looking for f prime number line. So we're looking for this number line that we did up here. So to find the values that we plot, we need to take the derivative. So the derivative is e to the x minus 2. First question, is this ever undefined? No, this is always defined. Is this ever 0? Well, let's see, e to the x would be 2. Take the natural log of both sides. So x is the natural log of 2. So our only critical value is natural log of 2. I'm going to label this f prime and plot the natural log of 2 and say the slope was 0 there. Now I need to test something to the left and then something to the right. So let's test maybe 0 to the left, because 0 is less than the natural. I think, let's actually plug that in. I don't think 0 is what I wanted to say. Natural log of 2 is 0.69, so yeah, we can test 0. So this is approximately 0.69. If I plug in 0, I'm going to get e to the 0 minus 2. E to the 0 is 1, 1 minus 2 is less than 0, so negative. Now test something to the right. We said this was 0.69, so maybe I'll plug in 1. So e to the 1 minus 2 is positive. From this number line, we're going to be able to read off everything. Here the slope was going negative, then it was 0 and positive, so let's go ahead and write that in just so it's more clear. So I have a local minimum at x equals the natural log of 2. I have no local max. Where is f of x increasing? And where is f of x decreasing? We'll see increasing corresponds to where the derivative is positive. So it's positive from natural log of 2 onwards. So natural log of 2 to infinity. Decreasing, that would be this area over here, so negative infinity to the natural log of 2. So from this number line, we're able to just read off everything. So let's do one more here. I want to find local maxes and mins and intervals increasing and decreasing for the function x over x minus 4. So I want to find the local maximums and minimums and increasing, decreasing, so that's talking about the first derivative. So let's see, what is the first derivative? Well, to find the first derivative, I'm going to have to use the quotient rule. So my u prime is 1, my v prime also 1. So this gives me x minus 4 minus x over x minus 4 squared. And let's simplify this just a little bit. Negative 4 over x minus 4 squared. Is this ever undefined? Definitely undefined where x is equal to 4. So it's undefined at x equals 4. Is it ever 0? Well, the only way this fraction could be 0 is if the numerator is 0, so no. So it's never 0. So on my number line, remember I'm going to label it f prime. I'm going to say that when x was equal to 4, the derivative was undefined. Now I'm going to pick something to the left and plug it in. So let's say 0. If I plug that in, I'll get negative 4 over 0 minus 4 squared, which is definitely negative. And then something to the right, maybe 5. So negative 4 over 5 minus 4 squared, also negative. So from this picture, do I have any local maximums or minimums? No, this is not a local max or a minimum, so no local maxes and mins. I would need the derivative to change for that, and I don't have it changing. When is it increasing? Well, this is never positive, so it's never increasing. And when is it decreasing? So f of x is decreasing from negative infinity to 4, and then from 4 to infinity. It's not decreasing at 4. The derivative is undefined there. So it's decreasing from negative infinity to 4, and then from 4 onwards. So that's increasing, decreasing, local maximums and minimums. This graph is going to tell you everything you need to know. So this is what we want to be really comfortable drawing.